So, hello! How are you? Oh, that was nice. So, today we are going to fool around a little bit with objects, making them in 3D and back to an object. So, how do we do that? I call it reverse engineering, but it's really not reverse engineering. It's just having a look at how things look like, taking an image of it, making a 3D object of that image, maybe using Fusion 360 or some other CAD program, and then 3D printing or milling it out on a CNC machine. So right now we have something going on my 3D printer. You can actually see that there's a wrench being printed out on the 3D printer. You can actually see a little image of it down in the left corner as well. And you can also see how it looked like when I took an image of this little wrench. This is a 15mm fastnøkkel, what we call it in Norwegian. And what I did, I just took an image of it, just straight above the image, trying to center it as much as possible to not get something called parallax when image gets kind of distorted near the sides. What I did then was re-importing that image into a CAD program called Autodesk Fusion 360. And then I actually scaled, there's a scale function here, so you can actually click calibrate and you can tell, for example, you can take that point and that point, and it actually tell how that is supposed to be. And you can scale the image pretty much dead on how it should look like in real life. And after you have the scales set up in Fusion, then it's possible to make a sketch. So a sketch is a 2D drawing, just like with pen and pencil, just with the CAD program instead. And then you can actually draw out what you see on the image. So you can sketch it out. And when you're finished sketching out the 2D object, then you actually have something you can extrude. Extrude is what you do when you take a 2D object and you pull it out in 3D space, so it actually fills out. Let's see how. Oh, I turned off body. But so when you extrude it, it looks like something like this. Except with I have something called the bevel edges on this one, just for the looks actually. Oh, hello Fusion, come on. There you go. So you can see the sketch laid above the image. You can see there's a 3D object above the 2D image. And the next thing you want to do when you extrude it, you want to make either a component of it, or just take the body and click make and 3D print. And then you just select what you want to 3D print and save the file. I already did that. And then you put it into your 3D printer software. There's tons of different software for this, but all of them are pretty basic. You import your STL file, you set up your feeds and speeds or temperatures, melting temperatures for the plastic, and how fast you want the machine to go. And you generate the file. And then you send the file over to the 3D printer. I actually have something called Octopi set up. It's just a Raspberry Pi, a little microcomputer set up with the 3D printer. It's finished now. So you can see I have a web control on my 3D printer. My chat has bugged out. There you go. So you have a web control, so you can remote control your 3D printer from a distance. Mine is actually another room, so I don't get all the fumes and noise from it to bother me all the time. Yeah, you can then you import your STL file into the software and you start printing, and after a while, this took around 1.5 hours, you're probably gonna get plastic from your 3D printer, something like this. This is actually something else. This is battery holders for an 18650 lithium polymer batteries. So I'm making battery packs from old laptop batteries. So I'm actually 3D printing. Oh, I'm actually 3D printing the holders that is supposed to. I'm just tearing off the raft. When you 3D print, you can choose to have something called a raft below your object, so it kind of sticks better to the 3D printer. But then when you're finished, it looks like this, and it actually fits pretty well. Let's see if I have some 18650 50 batteries. So these are recycled batteries from laptop batteries. And you can see it actually fits pretty nice in. I think I have some other ones. Just need to clean it up a little bit. Sometimes when you 3D print there's a little bit of excessive plastic around. And then you just put the batteries inside there and another raft on the other, another object on the other side, and you solder on the points, solder points, cables. And then you put on a lithium BMS charger, and then you have a battery pack. But that's not what I'm talking about right now. Right now we're talking about a wrench. All right, it's actually this wrench. So I'm just gonna go out to the 3D printer and get my plastic and see how far away I got using this technique. I'm really excited about seeing how much I kind of missed the original just by tracing an image. So I'll be back in 2 seconds. So I'm back again. I'm really excited about this. I have never tried it before, so anything could go wrong. What I'm most excited about is how far away from the original in size of dimension I will be, because it really depends on how your lens on the camera you're using to take the image from directly above distorts or wraps around the edges. So usually the center part of your image will be pretty exact, and depends on how distorted your lens is at the end, the corners of the image. It will be kind of wrapped. The sizes will be wrong and all that. But this really looks okay, actually. I will take off the raft, and it will be easier to see. But you have the 3D printed version, and you have the original. And when I put them above each other, they look very, very good, actually. The reason I started researching this was because I have a customer that wants me to cut out the insides of a Parallax foam for a lot of tools, and I'm trying to work out the best way to get the tools properly measured up the fastest way possible, and then cut them out inside a foam, so I can put the foam back inside the pellet case, and then the customer can put his tools inside the pellet case, and it fits perfectly. And that's why I need this to be in scale. It's not really to have a working wrench, it's just to have the proper sizing. But this looks very, very good. I'm just gonna pull off the raft now and try to clean it up a little bit so you can see it better. Feel free to ask me any questions on the chat. Yeah, I'm open for anything today. This is a very cool experiment. Oh, so if you just tune in, I took an image. I traced that image back into a CAD program, scaled it properly using just measuring. Just inside the image there was actually a little tool that tells me how big it is, and I just laid it up next to the wrench, and then I calibrated it in Fusion 360 using a calibrate function to get it to scale, and then I just drew above the image and then extruded it, and then I sent it to the 3D printer just to have a look on how far away from the scale I got. This looks very, very good. I wonder if I can actually, if I have a 15 millimeter. No, that wasn't 15. If I find a bolt that's the correct dimension, I can actually test the wrench. That would be cool. Using a 3D printed wrench, reversed engineered wrench, to actually tighten a bolt or something. But, I'm not really ready to find that 15 millimeter bolt right now. You can also print without using these rafts, but sometimes it depends on how big your design is. The design may come loose from the 3D printer. It can actually fall off during the multiple hour print, and that sucks a lot, because then you're gonna get a big ball of plastic just melting in the nozzle and maybe start a fire as well. So it's really not that good. Just need to get a knife. Try not to cut myself. I don't know what this is called in English, but in Norwegian it's called scalpel, and it's very sharp. So you really need to be careful. But these tools that the doctors use are very precise to do nice operations, and it's very nice to have a precise tool when you're working on something like this. I'm just trying to take off the inside of the raft right now. It really doesn't matter, we can just go like this. This is pretty much dead on, actually. This is very, very good. This is the first test as well. I never did this before. So apparently the scaling function inside Fusion 360 is very accurate, as long as you have an accurate measuring device. So we have our wrench. It's pretty much spot on. This is very, very nice. It's the same length, definitely. I can measure it up with a tool as well. And it's the same width, because when I lay them above each other, they're perfect. So, cool. Wonder how this looks like. This is also, this is spot on. It's supposed to be 15 millimeters wide, and it's 15 millimeters wide. So there you have it. If you really want to reverse engineer an object, or maybe make something else that fits with your object, then you start by, let's see if I can do it real time here. I have an application inside Windows 10 that's called Camera. In Norwegian it's called Camera, but it's the same. When you open up the camera, you can see your USB device, web camera or anything. Right now I'm just using another camera on a tripod, yeah, like that. And shit, and now I spilled Coca-Cola everywhere. Well, I need to fix that. And then you have something white or some great background. I'll be right back. So I'm back again. Had a little Coca-Cola accident here, spilled Coca-Cola over my keyboard. So let's hope it doesn't stop working while I'm doing this tutorial. So I cleaned it up now. what I want to show is how you actually can reverse engineer, or at least get proper measurement of an object, put that inside a CAD program, and then and then um, and then take that CAD drawing on further on to down to production, for example, with a 3D printer or CNC machine. Actually, I have both, but today I tested it out with a 3D printer because I really wanted to have a small plastic version of that just for scale. So you can basically make anything with a 3D printer today. So let's have a look. This is just a web camera, and that web camera is pointing down at a white surface, or at least there's some reflection there now, but it doesn't matter. So, and then we put down something for scale. I actually drew up some 5 centimeter lines already, but they're just for, there's Coca-Cola on the Coca-Cola everywhere today. So let's put it down, and let's make something. We already made a wrench, so let's try to make something else. I have a lot of these 4-cell BMS lithium chargers that I'm going to use for another marine project. I'm going to build battery packs, and along with some solar panels and stuff. They're going to take time lapses over several years, actually, out in the field. But I really need to draw this just for fun right now, but I need the scale. What I could do was just take a caliper or a measuring device of some kind and just measure out the size and the width, and maybe do that and be finished, and then put that further onto my project. But today we are going to do this the hard way, or the easy way. When things got sometimes there are designs that are a little bit harder to design. For example, is wrench. It's not really easy to get all the curves right and all the design. So we're gonna put this in the somewhere over like that. So there we have it. Let's take that image. Now we have everything we need. We have a scale, we have an image, and the object is in the center of the image, and that's very important when you do this, because there is something called parallax. When you get to the sides of the image, the aspect ratio and everything in the image gets wrong. All the dimensions get kind of screwed up when you go to the sides. So you have to have the camera in directly above the object you want to photograph, and you need it to be centered. So at least in the center third of the horizontal and center third of the vertical image. Never along these where the mouse are now, just in the center somewhere. And then when you take your image, then you kind of import it into, I'm using Fusion, but you can do this in SolidWorks or AutoCAD or whatever. So let's make a new sketch. We actually don't need that as well. We can just insert our image directly onto anything. Then you go Insert, Attached Canvas, and then you select your what space you're working in 3D. I'm working with the front always because that lays out perfectly with all CNC machines, and all the coordinates are perfect from scratch. So let's see if you can try and find this image. The camera builder, camera images, or the Windows 10 camera application stuffs everything into documents and camera images. So there we have it. Just gonna import it as it is. It doesn't matter right now the scale because we're gonna fix that now. So we go to the canvas and then we right click the image and then we go calibrate. So let's find our 0 or something similar. 5 centimeters and then 1.5 centimeters, for example, like that. And then we tell Fusion how big that is supposed to be, and it's supposed to be 10 centimeters wide. And then it scales up the image to fit that scale. So if I draw a rectangle here now, you can see that it's almost, it's for 47 millimeters times 56 millimeters wide. Let's just have a quick look with our measuring device and see how far away we are. I'll switch to full screen here. So we have some focus problems with this lens. Focus. There we go. So this was the laying up. So this is supposed to be 40. How much is it? 48. Depends on 48 times 55. 50. Was it dead on or 56 millimeter? And what did I say? Let's see here. So we measured that side first, that one, and that was supposed to be 47 times 50, almost 56. Yeah, that looks pretty good. How much is that? It's impossible to watch them as webcam images. 48. Yeah, this is very, very good. Just with a quick calibration from that image, we can actually see that we're pretty much dead on size-wise. So the only thing we need to do then is draw it up. You can see the image here is a little bit rotated, so we can either draw a line or we can actually go freehand on this. So let's really go into this the old school way. Let's just draw the lines. My web camera is too big, so you can't see what I'm doing. So much better. So I'm just going freehand lines now, just drawing up what I think it looks like. And then what I can do, just to make sure all the lines are perpendicular to each other or parallel, you can say that line should be parallel to that line, and Fusion will actually fix that for you. So now those two lines are parallel. They're exactly matched to each other. And let's do the same with the above lines. And you can say that line should be perpendicular to that one. And if you do the same down here, you have your square. This should be perfect square now. I saw there was an error there somewhere. You can actually over constrain your image with Fusion, so it kind of bugs out. But so we have our sketch now. We can remove the back image. We have our square, and that square, if we use the dimension tool just to get an impression of how big things are. Dimension, come on. We can do this, maybe 48, yeah. Times 55, almost 56. So let's extrude this. We push E for extrude, and then we make it, how big is this? Maybe probably a couple of millimeters. Let's make it as big as all the components are, because I'm going to fit this object into another object later on. So I'm going to use this CAD drawing as a cutting tool to actually cut into the other box I'm making and get a perfect fit. So let's make it as big as this one, or high as this one is. It's around 7 millimeters. So let's make it 7 millimeters high. And this is our, this is our circuit board, or at least a model of it. And it's modeled from an image. There's tons of other ways to do this. I'm just illustrating this way now because this is a very, very good way to reverse engineer complex objects that you're not able to actually measure out. Let's do it with something more difficult later on. So this is our, let's save this. This is our 4-cell lithium 18650 BMS charging PCB. That's good. What we can do now is just send it to 3D print and see how far away from the original we got. So you can actually go 3D print, select, hi, okay, save it to somewhere. Cncgarage. Let's put it inside 3D print, yeah, and we call it 4-cell PCB, yeah. And then we go open our 3D printer software. We just import our STL file. We have to find it first. There it is. It doesn't look like much, but the important thing is the scaling, and that's what we're really interested in when we're doing these kinds of 4 millimeter. Yeah, 210 degrees. Yes. Save the file. Go. G-code. Yes. What we're doing next is we're running something called Octopi, Octoprint. It's a Raspberry Pi connected to the 3D printer, and that 3D print that makes the 3D printer available from your local area network. So you can upload the files directly to the 3D printer without taking the SD cards out of the 3D printer, go and put it into your computer and put the file up and back again. So 4-cell PCB, yes, that's the one. Let's have a look on this, how this looks like. Oh, this is wrong. This is the wrench. Oh, I loaded the wrong one. So I need to load this one. 4-cell PCB. Load. Yes. G-code viewer. You can actually see how this will turn out layer by layer on the 3D printer. Cool. Very cool. You also have inside this, you have a time-lapse function, so you can actually have a camera connected. That's what I have. You can see my camera. You have seen it already. I just streamed it out. It's kind of low resolution here, but it doesn't matter because it normally just makes a time-lapse video, so you can download later on and show. So just let us download that wrench we just made. This is our wrench. This is the first time I'm opening this, so PLC really don't like these files. It's so fast. It's only 1 frame per set height change, so it goes very, very fast. Yeah, but it does make time-lapse images. There's also something called the Octolapse that actually makes really beautiful time-lapse images for your 3D printer. What it does, it actually takes an image every time the 3D printer is outside of your camera position, so it looks like this. The files are just growing. But that's, yeah, they move the 3D printer to the exact same position before taking the image and doing the next layer all the time. It takes a little bit longer to 3D print, but the cool thing is that it looks awesome. So when you generate these kind of files, it's really cool to have this to see what this. I think this was actually a 48-hour 3D print or something. It's pretty cool. Lapse. You can download that as well. I haven't yet. Just set up my P. So I'm just running the internal time-lapse generator. It's good enough for now. So let's start printing. We need to get this running. Just preheating the printer. You can actually see that these graphs are representing the temperatures on the 3D printer. So what I did now, I set the extruder to 210 degrees, and I set the bed to 60, and it starts to heat up. You can see the lines are slowly going up and try and match my criteria. It's pretty cool. So we can start the print now. Can have a look on the printer is just chilling out in the corner there. I can home the printer. What that does is just it sends all the axis of the printer down into the homing switches, so it knows where to start. So you really don't need to do this normally, because the 3D printer handles all that crap itself. It was just for fun. So this looks like it's gonna take 1 hour to print this 6mm square. It's probably gonna take a little bit less, but it really doesn't matter. It's just for fun now, just to have something to do while we're doing some reverse engineering. So this is printing. This will be probably finished by the time I'm finished with the next one. So let's just keep that running. I just have to go fetch some stuff. I'll be back in 1 second. 1 second, maybe 1 minute. So, back again. Let's see if we can do this one more time. Here's another tool. This one is a little bit more complex than that squared circuit board. So let's see if we can use the same technique. What we're doing is we take an image of the object. Jesus, sorry. You know, on the radio channels, they have a button in front of them that they can push when they sneeze, so it mutes automatically and don't kill all the radios around the world. I should have the same. Or I should just not be sick. Anyways, so this tool is this is actually an RJ45 network cable plier. It's used to squeeze on the RJ45 network plugs on the Cat6 or Cat5 cables and makes network cables. So we're going to take an image of this. We're going to use our standard web camera software that actually comes within Windows 10. Just search for camera, just push start menu and write camera, and it comes up. And connect your whatever camera you have. Try to have a camera that has a zoom function. There's a reason why you like zoom, and that's when you zoom into an image, you kind of focuses on the center of your lens. Let me show you. This is a lens this is a zoom lens. It's a USB camera from eBay somewhere. It's called ELP. Just search for ELP USB camera, Sony MX322 or something. Yeah, I can give you the link later on. So the thing is here, there's a little lens on the camera that makes you zoom, and then you can set focus manually. And that kind of gets rid of some of the wide angle cropping you have on the sides. So, and it's much easier to do this then. Try to keep your object in the center of the vertical and center of the horizontal part of your camera lens, like this. It kind of fills out the center now, right? Not have it over there or over there, or because then it kind of distorts more. So it looks pretty good. The lighting here is not the best one for doing this, but it's good enough. Don't need to be the best all the time. You just need to have exactly what you need to do the job. So we have our measuring device. We have the focus. Looks pretty okay. Looks like we're hitting the spot there somewhere. The camera is in center, top center, directly above our object. And we have our measuring device, and we just grab an image. And then let's see how this is doing. Maybe they started 3D printing. Yep, you can see the other one we drew earlier. It's working now. So let's do this all over. Make a new sketch inside Fusion 360. You know, Fusion 360 is free for our makers, so you can download it for free and start off. And it's really not hard. So you make a new project. You go to Insert, Attach Canvas, and you select your image. And you find your image inside the standard folder in Windows. There it is. And then you select which plane, 3D plane you want to work on. I really want the front plane, so that's good. And we don't care about scale right now. We just need to import it as is, because we're gonna do the scale now. So we show our canvas, and then we right click on this canvas and we choose calibrate. And we go from somewhere we like, maybe 2 centimeters this time. It's pretty much in the center of the image. Well, that's what I'm looking for when I do this. I try to be as close to the object as possible when I do the scaling. the first point 2 centimeters, and the second point should be 12 centimeters then. So then we have a 10 centimeter calibration spot. And then we tell Fusion that it's actually 10 centimeters. 10 centimeters. Okay. Fusion scales up the image. You can see it's smart to have a bigger resolution on the camera when you're doing this, but this is okay for now. So we have our image. It's to scale. So if I draw something here now, and then if I go from 2 centimeters to 4 centimeters, it should be, yeah, around 2 centimeters. See? Yeah, it looks pretty good. Looks like a little bit off. Let's do the calibration one more time. So we go from maybe 2 centimeters. We can go further actually. We can go to whatever. We can go to 17 maybe. And we try to have a straight line. So this should be 15 centimeters then. And you can see it's already suggesting that it's pretty close to 15 centimeters. We just need to tighten it up a little bit. Let's see now. If I drew a line from here to here, that should be 1 centimeter. Close enough. Yeah, this looks very good. We can just do a control measurement over here. You can see the camera lens is fucked up all in the corners here. But so we have some lines here. There we have. So still 1 centimeters. Looks good. So it looks like everything is kind of proportional. This is not exact science. This is as close as you get without 3D scanning the object or using measurements to actually measure out the entire object. And this is much, much faster. Of course, there are other ways of doing this as well, but I think this works pretty good. Let's have a look at this subject again. So it's network plug crimping tool. Now we're drawing along that line, so it should be nice and straight. You can see me all the round corners I will go back and draw later on. So oh, don't be afraid of saying hello on the chat. You can see that Kim Daniel is making a smiley face. Hello, Kim Daniel. Haven't seen you in a while. You should do something about that. So all the rounded corners is better to do with another spline tool or something else. We have our spline tool here. Let's see if we can use that. You can see why it's smart to use another tool to draw the other lines. You just mark out some spots along the curve and it kind of calculates out the rest itself. need to, oh, there it is. Another curve, another spline. I really like working with the spline tool. It's, you can, you know, if you have something, let's say you don't like the curve you made, you can go in and edit it afterwards as well, just to try and fix it. You can move the points, or you can move the size of the curve, or you can move the angle of the curve. And you can actually write, I think you can also tell it what radius you want the circle to be. It's very, very nice tool. So let's do this. Yeah, good enough. Good enough. Remember, this is when you do these kinds of things, you're probably looking at altering it to make it your own, or do some other stuff with it later on anyways. So it's really not super important to have it dead on the sizes on all that. It's probably good enough for what you're doing, because you're probably going to do some changes anyway. When you do this, let's see if you have if you want to retrace, for example, this one. This is a shelf holder. If you want to redraw this one, the only two important the two important holes you really need to get right is the dimensions of the circular holes that you put your screw inside, because it's normally connected to something, and that you can't change the screws if you're just making that part and not the other part. And also the distance between the holes, that's the other important part. Everything else, it really doesn't matter how this part looks like, as long as you have the dimensions of the hole and the size between the holes, the arrangement of the holes in yeah, in the right way. Then you can actually make a new product that's kind of different in size, or different in yeah, in any way you want, but still fits perfectly with the opposing components. So let's go back to this. Let's say theoretically that I want to mill this out in you know, foam. When you have inside Paley cases, you have foam. I think I have some Paley cases here. I'm not sure what's in this Paley case, but it's only one way to find out. Huh. Yeah, there's some foam. It's so much stuff in there. Yeah, you know, foam. You can use a CNC machine to carve out the holes when you you can put the tools into the holes, and then you. Right now we basically have our sketch. If you just want to carve out the hole, we have everything we need already. If you want to make that tool all over again, then we need to be drawing out everything else as well. But right now we're just gonna make it like when we do Paley cases or something like that. So we're just gonna extrude all the outer dimensions of the tool to have let's call it a cutting tool. So let's say we have it's probably 20 millimeters, maybe more. Let's say 30 millimeters thick. And we're making a new body using the extrude tool from this. So now we went from an image to a 3D object. So we can turn off the back image. And we can actually kind of see the contours of it's probably gonna be like that. No, my web camera is mirrored, so it's almost like that, So and now we can, let's say we have a Paley case design. You know what a Paley case is? Paley case. So this is a Paley case. You have the foam inside, and you carve out the foam to place stuff in them like this. This is carved out from the outer outer, what do you call it? Outer layer of the outer borders of the tool, and then you carve out the rest, and it fits perfectly. And sometimes you want to leave room for, let's say, you can actually put a finger between and pull it out. Um, so why is the internet full of weapons? Tools. What's wrong with a screwdriver? So this is actually pretty much close to what our customer wants. He wants to have a pellet case like this with a lot of shelves in them and custom cut foam for all his tools. So we're gonna make this actually next week. And yeah, we can just imagine how this will turn out. So let's say we make a new sketch with the size of our pellet case. I'm just gonna suggest some sizes now. Let's say that it's 30 centimeters wide by 40 centimeters, like that. This is our pellet case inside. We extrude that and say, oh, it's not 40 centimeters, it's 40 millimeters, maybe. I don't have the exact dimension, so I'm just making something up. So just for appearance, let's change the color of our tool to something blue or something, just so we can understand what's what. And then our pellet case foam can just stay the color it is, or it can be black or whatever. Yeah. So what we want to do when we have a lot of tools, then we want to lay them out inside our pellet case. So we're just gonna move it. Oh shit, it's the wrong body. That's the right one. Move. Just gonna move that inside here until we kind of work out where it's gonna be. It's gonna be probably flush to the top, so like that. And then we are going to maybe rotate it. Maybe we decided that it's probably better to have it the other way. Yeah, something like that. Or maybe sometimes you kind of, oh, we want to use the entire size of the pellet case, so you kind of squeeze it into the edges, or just make the best size of it. It's almost like making gingerbread figures. You just kind of lay it all out on the gingerbread before you cut it and try to make the most space out of it so you get the most cookies. And then let's make a couple of more of these. Copy, paste. Yeah, sure. We have another one. We do the same here. It's like, okay, we can either do it like that and try to make the most out of the space, or we can make it look good. Sometimes customers really are more obsessed with it looking good than actually making the most space out of one. So let's make it kind of a little bit more better looking at, because move, rotate, something like that maybe. We align the tools up like that, and maybe one more. This is just an example. Paste. So over here maybe the same spacing between them. You can actually use there's another tool for making a lot of the same object. You can actually test that out now. So let's just rotate this again like that, and I'll show you a new tool. So we have our body, we have one body, and we can use something called a pattern. Let's make a rectangular pattern today. This is what I use when I'm milling out more than one object on a CNC machine. So I'm using a rectangular pattern, and I'm telling the software what object I want to come on. This is our object, and I want to make 3 of those quantity, and I want it to go in that direction like that. And you can see the spacing between the objects kind of sorts out automatically now. This is very interesting. 1, 2, 3, 4. Ah, that's good. And we can have one more direction if we want. If there were room for more above this one, we can do the other direction as well. We can just, for illustration now, just show how that would look like. This is, oh shit, that went well. So like that. And we have, we need one more direction, 3. And we want it to be the other way, like that. So you can make a rectangular pattern. So you can make 2 directions at the same time. We're not going to do that right now, but we are going to do that way. So now we have our inside our Paley case, and we have 3 tools put up on those with the exact same spacing between them, so it looks good. And now we need to cut the foam square with those tools. But before we do that, we probably going to do something else. We want it to be a little bit more clearance between our objects. But now just leave it at that now. We can use something called offset to make sure we have more room than the exact size of the tool. But let's just skip that for now. So we want to cut using these 1, 2, 3. Let's call this Paley insert. So we want to cut the hole in the square at the size of our tools. So we use the combine tool, and we select the square, or the piece we are going to cut into, and then we select something they call tool bodies. A tool bodies is exactly our objects. And then we go cut. You can see it actually cuts a hole now. You can see it cuts a hole by the size of the selected tools, and we can make a new component from that, and we're gonna keep our original files as well. And now we can unselect all this, and we can see our new component. This is pretty cool. Let's do a render of this, maybe. So this is our Paley case insert. It's a very rough sketch, but I think you kind of understand the idea. You can have whatever color you want. Red, maybe. Every time I click in canvas render, the stream always falls down. So let's try that now. I didn't crash. It's the first time. What happens now is Fusion 360 is trying to render out this image. And it improves the render each step, you can see down here. So this is iteration number 24, 25, and it goes up to excellent, and it gets better, 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 better. The lighting gets better, blah, 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 blah. That's the same thing that happens when you push the render tool, but then you can't see the process. But so we did this now. We went from this network cable wrench tool to let's find the object, this component, there you go, to this, the outer line sketch. We went through an inline canvas. We drew it from an image first. We drew the body out from the image, and then we moved it out into a Paley case. And then we made a new component with the cutout from the Paley case. You can also do, if you know that you want the room for a finger, for example, you can, shit, I need to cut this. I need a room for my to get something out of this, I need something like that. So you can actually put the finger down and lift the tool up or something. And then when you're finished with the entire shelf, then you send this component to something called a CAM software. It's actually inside Fusion as well. And then you make a new setup, and then you say, I have this. I don't want these bodies. I just want these. I only want these components. I want this component. Yeah. And then I say box point down there. My 3D coordination tool looks good. And I go, no, yeah, sure. Outside the offset, like that. And then I go to pocket clearing. I choose my bit to mill out with. So I find, for example, a big bit, something like the one I'm having here. This is a 10 millimeter cutting tool. It's an end mill because it's flat in the end. It's called end mill. It has two flutes. A flute is what you see the cornered sharp tool that's actually digging into. So that's actually digging into the material. I can show you another way because the Cncgarage logo is finally finished, and it looks like this. Anybody guess where I got my inspiration from? It's a two-flute end mill tool. If you see that tool here from the center, you can actually see it has two cutting sides. This is one of them, and that's the other one, and it spins around. So every time it spins around, it kind of carves out a little bit, a little bit, a little bit, just like a saw. Turning, yeah, just a normal blade saw has a lot of these flutes, if you can call them that. This end mill only have two, like that and that. And then let's say we go for a 6 millimeter end mill, yeah. And we have to make sure it's long enough to dig directly into the material, and it's not, so we make it longer. So we're just gonna set up this tool. We have two flutes. It has to be at least 40 centimeters. That should do it. 3.5 meters. That looks a little bit overkill. So 6 millimeter diameter, and yeah, something like that. We have to make this match your actual hardware. But for now, we're just gonna illustrate. I have a 6 millimeter end mill that looks almost like this. And then we set out what we want to carve out. We want to carve out inside this green square. We want to carve out everything, all the holes here, we want to carve them out. So we set out a 3D pocketing clearing cam process at the toolpath process, and we make sure it digs all the way down that it needs to, and we restrict it to never go more than, this is foam, so we can actually go the entire length and a little bit more. Let's say 6 millimeter at a time. We never allow it to go more than 6 millimeter down, do it work, and then go 6 more millimeter down. So that's our maximum. So the blue lines here are how the tool is moving inside our material to remove all the material that's not supposed to be there. We can simulate this now, so we can actually see how this works. The gray spot there is our milling tool. You can see it digs down into the material like that, and it starts carving out 6 millimeter depth maximum, and it works, and it goes back and forth and back and forth and blah blah blah, and it takes a lot of time. It depends on how fast the machine can physically go without breaking something. In foam, you can go very fast. but it still takes some time. So it carves out now. You can see it carves out after the drawing, but you can see it kind of leaves something inside here. You can see, well, you could see, yeah, there's it a little bit. You can see it didn't carve all the way out into how it should, so it kind of misses something there, and that's because the diameter of the tool is bigger than the hole it's supposed to dig into, so we have to use a smaller bit to get cut out that little part, or we have to draw it another way to make the hole bigger. So according to this takes 42 minutes now, but we can definitely speed that up. Let's go as fast as the machine can go, 18,000 RPMs, and we can go probably like 4,000 millimeters per minute at least. And we can plunge down if we want fast, because it really doesn't matter. And when we do a ramp, we can go at least 20 degrees. Yeah, sure. And then it goes from 40 to 14 minutes. So this entire process takes 14 minutes now with a CNC machine. That's not too bad. But we still have some cleanup to do, because we could see that we were missing our hole. Simulate. You can see what it's supposed to carve out, and you can see it's kind of missing a little bit there. So we have to either go for a smaller end mill, smaller tool to get inside the diameter hole, or we can go back with a smaller tool later on, or we can actually make that hole bigger in the design. We can go back to the model and we can redraw this. We can make sure we know that since this is for a foam for tool inside pelly case, so it really doesn't matter if we were missing that little spot, the tool is still gonna stay down, right? So we can just edit that away, and it's still going to look okay, and it's going to be much faster for us to carve out. Let's see, just run the same cam process again now, regenerate the tool path so it calculates all over again. You can see it's not missing anything now. It doesn't have to go into a smaller diameter circle than the tool is, so it's not missing anything. And still the tool is gonna lay down perfectly. Nobody's ever going to know. And that saves us for a tool change. A tool change is when you take one bit out of the machine and then you put another one in, and then you start the machine again. It complicates things, it takes a longer time, and costs more in tooling because you're using more bits, and it gets more costly for the customer in the end. And we really want to be effective. We want to take as little time as possible when we do this, so that it gets so the customer gets the cheapest possible result at the best quality he wants to pay for. Because in the end, that's what it's all about. If the customer wants that corner, well, I'll fix that, no problem. But usually, it's everything is it's something between price and quality. And when it comes to this, for inside cutting in a foam, there's no precision needed to do the job it's going to do. The tool is going to fit inside there anyway, so it's probably better off for the customer just to lose that little square and save money. Because when you do this, let's say let's take a look at this image. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 shelves or something. 10 shelves, and if this process takes like maybe 14 minutes to mill, maybe 10, 15 minutes to set up. That's half an hour. Half an hour is costly when you have to set up the machine, you have to blah 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 blah. If you can save a little bit of time everywhere, the prices go down. It's much more understandable for the client to pay up for what's actually needed, and trying to save money where it's good. So interesting. We went from an object to an image. There's the image. And we went from an image to back to a 3D sketch of that. Let's see, 3D sketch of our object, and we made a foam insert in this correct size, and we used our tools to cut out the holes inside our pill case, and then we put that into a CAM software. Um, and we made the tool paths for a CNC machine to actually carve this out in foam. The drawing process is probably the most time consuming here in this entire process, because there's a lot of drawing and you're only going to mill this out once, probably, unless you're making thousands of the same sizes of these. And that's when it kind of gets cost effective to use a CNC machine. When um, you're making more than one of anything, then you save money. Then you can do it much faster and better and more precise than a person can do repetitive work. But when you're making one of something, then the costs of drawing it the first time kind of exceeds the cost of making it the first time. But the next time you're making it, you you have already taken the time and the money to actually draw it out, and then you can make 1, 10, 100,000, 10,000, a million objects for almost no money at all, because the time to make one of these takes like a half an hour to cut out. And then you can imagine if my CNC machine is big. Well, it's not that big. It's like 2.5 meter by 1.3 meters, and you can actually see the live stream now. So you can see this is my CNC machine. This is from another broadcast. You can see you have a lot of room here. So if we are going to mill out these in foam inserts, we can actually fill that entire table with foam, and we can probably cut out, I'm just guessing now, if it's 4 by 40 centimeters by 40 centimeters, then you have room. You have 2.5 meter one way and 1.3 meters the other way. You can probably cut out like 20 at the same time, and it doesn't take that much longer to cut out. It's just the cost of the milling process. So if you do this, and let's multiply this. So we have our process we are going to mill, and let's make more at the same time. So we make a new pattern, and we say we have a linear pattern. We want 2 directions. We want that direction and that direction. And we want to have 400 millimeters of clearance between. And we want to do 3 beside each other. And then we want additional direction. And that is that way. Like that. And then we go 400 millimeters that way. Direction 2, come on. It doesn't want to play now. Oh, it does. So let's make that above that one. And then you make maybe something like that. You have to calculate this, but I'm just showing now. Something like that. You can probably make that many on my CNC machine. I don't know. And let's see how much time that takes. Face spacing cannot be negative. Well, it could. I actually just did that. Anyway, so our pattern, let's see how much time this takes total. It takes 4 hours. So no, sorry, it doesn't. It takes total feed time Machining time 4 hours and 15 minutes to make, yeah, like 1 2 3 and 1 2 3 4 5 6 6 by 3 6 ganger 3 hvor mye da? 18, is it? 6 ganger 3 18, yeah. So to make 18 of these Parallax inserts takes 4 hours. And then you can just switch the sheet, taking like half an hour to clean up the old one and put in a new one and change the tooling maybe and set the machine up again. And then you can make 18 new ones of these Parallax inserts for 4 new hours. And that kind of makes a lot of sense to use a CNC machine for, because when if you're gonna do this manually, you're gonna just stand there and carve out forever. Cool. So that's how it is. Let's see how our 3D printing is going. I know we set a 3D printer to do some stuff. It's still working. It's making a square. Squares are awesome. Let's have a little look on how it's working. So it has been printing for 44 minutes and it says that it has 1.5 hours left and it's 31% finished. And the reason why it takes longer than it's suggested at the start is probably that's where it is right now. Actually, that's pretty cool. You can see it's making that square. It's filling out inside that square, layer by layer. It's pretty cool. And you can see when it's finished with that, it's going to scale this down again. The next layer is going to be like this, and that, and that, and that, and makes honeycombs. And then the top layer, and it's finished. So it has some time left. And the reason why it lays on something called a raft at first, and the raft you can see is bigger than the square going above it. So the raft is big and the square is smaller. And that's just to make sure the 3D print doesn't come loose from the 3D printer plate, the black one in the image there. Cool. So we went through some stuff today. Hopefully you learned something. How to reverse engineer designs from an image, drawing it in a CAD program, and then 3D printing or milling it out on the CNC machine. Cool. If you have any questions, feel free to leave me a message at the chat. It doesn't matter if you're watching the playback afterwards. I can still read your chat questions. Remember to subscribe to my YouTube channel. I really appreciate that. You can go to Cncgarage.org and you will be forwarded into my YouTube account. So if you don't remember the YouTube account name, you can just go to Cncgarage.org or .net and you will be forwarded into my YouTube account. It looks like this. I will put out more tutorials after a while. Yeah, just tune in. Sometimes I mill out stuff with this machine, the CNC machine, like that. That goes crazy fast. It's very fun. This is actually aged HDPE plastic, 20 millimeters. And you can see I'm making a lot of components on the same plate. I'm actually making 96 components at the same plate here. It took 30, almost 40 hours in total because it's a two-sided mill. But it got very nice. Yeah, you can see I'm actually using a 10 millimeter end mill here. So you can see it's moving a lot of material. Look at that. It almost looks like a water stream. That's pretty cool. You can find all of these videos. These were live broadcasts, just sent live when I was milling. So I wasn't doing any chats or anything. I was just focusing on getting this done in the garage. But you can watch this in the playback on YouTube or on the Facebook CNC Garage Facebook page. It's pretty cool. You can see it's a lot of plastic being removed at very intense speeds. So remember, subscribe. I really appreciate that. That's the best you can do ever to help me out, because I really want to reach 1,000 subscribers, because then I get really happy. Cool. Have a nice day. Have a nice weekend. I'll see you later. Bye.